I'm going to draw a coefficient of lift versus angle of attack graph. So this is going to be the y-axis is going to be coefficient of lift, and the x-axis is going to be AoA or angle of attack or alpha. So we're going to have a 0 right here. So x is going to be angle of attack or alpha, and CL is going to be the coefficient of lift. So for a non-symmetrical airfoil, also known as a positively cambered airfoil, the CL versus alpha graph is going to look like something like this. And you see that this peak up here, that is going to be your critical angle of attack. So this is going to be alpha critical. And this is going to be, highest point right here is going to be CL max. And that's where the stall happens. Okay, so once beyond that point, it just the air is separating, it's not producing much lift, and the wing is stalled. What we usually don't see is the other side of the graph. There's another side right here that on the left side that has a peak on the negative side. So this is going to be just going to be a positive stall and a negative stall. This side is going to be the positive, side is going to be the negative. So this is going to be the CL max negative. This is going to be the upper side, CL max positive, and this is going to be the negative critical angle of attack. So that's when I stall negative. So this is going to be the negative stall, and this is going to be the positive stall. And there's a point here that is an important point, and is when CL, coefficient of lift, equals 0. We remember the lift equation is 1/2 rho v squared SCL. So what happens here if CL equals 0, then lift is 0. You're right, I'm not producing any lift. That point is very important. It's the point of 0 lift. So this is when I have 0 lift. And this is an important point because I don't have lift. So lift is 0. I'm not producing any lift. So I am falling down. I am following a parabolic trajectory down. But I'm also producing less drag because if I'm not producing lift, I'm not producing induced drag. So no induced drag. At 0 lift. Total drag is less, so it's the minimum amount of drag that I can have. I can pick up the highest amount of energy, and something that is very important is that I am in between the positive stall and the negative stall, so I'm as far away as I can be from either stall. So at 0g, I cannot stall. Airplane cannot stall at 0g. And the other important part is that the G loading is 0, meaning I cannot exceed the limit load factor either. Can't overstress the airplane, can't exceed the G's because the G loading is 0. So that's going to allow me to pick up the maximum amount of energy the fastest. Now that's not straight and level. In straight and level, I'm producing as much lift as I have weight. At zero lift, I'm not going up, I'm going down. But it's a beneficial point if I want to recover from an unusual attitude or something. We usually don't experience zero G or zero lift. We're usually very close to 1G or lift equals weight most of the time. Now I'm going to show you what the graph will look like if my airplane had a symmetrical airfoil. Aerobatic airplanes have symmetrical airfoils. And if the airplane had a symmetrical airfoil,